Hello, I'm Gernot Heiser from UNSW Sydney and also representing the seL4 Foundation. Welcome to my talk on seL4 on RISC V. The seL4 community this year had a major highlight, and it had to do with RISC V. In fact, it was the formal verification of seL4 on the RISC V architecture, and I'll tell you what that means. First, not everyone is familiar with seL4, so what is it? It is an open source, high performance operating system microkernel that is also particularly known for its high assurance. So an operating system microkernel means it is a piece of software that runs at the heart of every system, and it controls everything. And in particular, it means it runs in the privilege mode of the hardware. And it's a microkernel because that amount of privilege code is minimized to maximize modularity of your system. It's the world's fastest of its kind, and I'll give you some backing for that claim. And this is what it's mostly famous for. It is the most comprehensively assured in the sense of strong mathematical proof operating system. And what is particularly cool, it's open source. It's available on GitHub under the GPL v2 license, exactly the same license conditions as Linux. So the combination of these things make seL4 unique and make it a particularly useful system for building, or promising system for building, really high assurance safety or security critical systems. And many people are already doing that. It is already deployed across a range of sectors: defense applications, space applications, industrial control, any avionics systems, and other safety and security critical use cases. And its applications are growing pretty much by the day. We just had the third annual seL4 summit, and over 3 days, people talked about their deployments of seL4. It was quite exciting. Okay, so I made some claims about performance, which a lot of people claim. What do I mean here? Well, there's actually some independent data on some performance comparisons. Not complete, because most people don't let you measure their performance because they would look bad compared to seL4. But some researchers over the past 2 years done a performance comparison of several open source microkernels, including seL4. So the numbers you see on this table are IPC latency, so the latency in cycles of sending a message from one address space to another. So that means small is good. And as you can see, seL4 is by far the smallest of those. There's one thing that sticks out. At the time this one paper was written, we had a performance degradation, a performance regression, which degraded our performance by about 50%. That was still a factor of 2 faster than the next fastest system. So we have some leeway. Obviously, there's lots of other microkernels around, which I can't present data here, but I know from various experience talking with customers, doing evaluations, etc., that the commercial systems you may be familiar with are performance-wise more like Zircon than like seL4. So basically about an order of magnitude slower. That's quite significant. Okay, this is why I, without feeling ashamed, claim it's the world's fastest microkernel. No one ever dared to contradict me. Please do if you have any hard numbers to contradict that. So that's one thing, performance. The one thing that really makes seL4 well known is its mathematical assurance story. So it has actual mathematical proofs of correctness, and I'll explain a little bit what that means. So seL4 is written in C with a minimum amount of assembler, but it's 95% C. And the proof is about the C implementation. For seL4, we have an abstract model, which is written in a mathematical language and very precisely defines the effect of any operations the kernel may make under any circumstances. So it's a complete functional operational description of the kernel functionality. And what our proofs mean, or what the core of our proofs mean, is functional correctness, which means the C implementation of the kernel is a correct implementation of this abstract model. So in a very strict mathematical proven way, seL4 is bug-free. There's a second proof step that goes to the binary that shows that the binary is actually a correct translation of that C code, which means we don't have to rely on the correctness of the compiler. We can use standard GCC with all its bugs and then run the toolchain over it, and it says, yes, the binary is correct. And because these two proofs are linked, we know that the binary, which is the code that runs on the actual silicon, is a correct refinement, a correct implementation of this abstract model. So bug-free to the binary. And then there's further proofs that show that the abstract model is actually good in a strict sense, meaning we can prove that this model can enforce the standard CIA security requirements. And in that sense, it is possible to build provably secure system on seL4. There's no other system with such a comprehensive proof story. And while seL4 was the first one with this functional correctness proof, there's meanwhile a few others. Most of them are toys. And none of those has capability-based protection, which is the core thing you want to have for reasoning about security, because it gives you fine-grained control over access. Ask me offline if you're interested in more detail. So this core functional correctness proof is what we have now done for RISC V. So seL4 is now the first and only proven correctly implemented operating system kernel on the RISC V architecture. And we are working on the translation correctness, and this is few months away. I really hope we will be able to finish it before the end of the year. If not, then very early next year. So we are close there as well. And then we have the complete correctness story for seL4 on RISC V. What do those proofs mean? Well, they, in particular, as I already explained, it says that the behavior of the C code is consistent with what the spec says. And that's a very powerful property, because it means that any further reasoning about the system can be done at the abstract level rather than the C code. So you can ignore the C code for any further reasoning because you know it's doing the right thing. And then there's a lot of implications from that. For example, all these typical attack vectors on operating systems are categorically ruled out by mathematical proof. So we will never have a null pointer dereference, an out-of-bound access, etc. Very nice to have. And a few other nice properties, for example, everything terminates, everything is finite, access control is decidable, etc. So this is what we have now for RISC V. And the question is, what you will probably be asking is, okay, did we learn anything interesting about RISC V? It may not surprise you that we learned one lesson, that is regularity is good. And RISC V is a very regular architecture, and that is immensely helpful. So the things we struggle with mostly, typically during verification, is the page table structures tend to be irregular. There may be differences between kernel and user level page tables. There may be different formats and different levels of the page table. None of this crap exists on RISC V. It's all neat. The ISA is very regular in other ways. For example, there's very little difference in the ISA between the 32 and the 64-bit version. And this table shows the implication of that. It's quite enormous. So what this shows is, on the three main architectures, how much of the kernel code is common and how much is mode specific, 64 or 32-bit. And on ARM and x86, the common code of the kernel that is independent of the word size is about between half and 2/3 of the kernel. In RISC V, it's 95%. That's a huge simplification. It means you basically do the work once, and for one word size, and then doing the other word size is pretty straightforward and quick. We also have a much smaller kernel. So this shows the kernel code size in terms of functions, but also more importantly, in terms of lines of code. And normalized to seL4, to RISC-V, ARM is almost 3 times as big, x86 is 3.5 times as big. So the regularity of the RISC-V instruction set architecture leads to a much simpler kernel. And that is a massive advantage, particularly when you want to get a correct one. And in particular, when you want to prove it's correct. And this is a very rough comparison of proof cost, in terms of person years, effort required to verify the kernel. I put the ARM v7 one in brackets because this was our first verification and we had to learn a lot. So this unsurprisingly took way longer than the others. But between RISC-V and x86, we're about almost a factor 1.5 to 2 faster than on x86. This is a direct result of the simpler kernel, which is a direct result of the regularity of the architecture. One interesting thing is that RISC-V specifies the clock as part of the ISA, which is really nice because that takes away a lot of complexity. And we certainly hope that the same will happen for the interrupt controller. So please specify the interrupt controller as part of the ISA, so we have only one to deal with. That would be awesome. Of course, one awesome advantage of RISC-V is its ISA is formally specified and the formal spec is the master. And that really helps for the binary correctness proof. So in the binary correctness, what do we prove? We have a C code that gets compiled by compiling to binary, and we sort of want to see that it's correct. But really what we need to prove is not the actual C source being correctly translated, but the formalized C, which is the thing we deal with in our proofs. And in particular, the function correctness proof, they prove the formalized C correct, not the original C source. So what we need is a proof that shows the binary code is a correct translation of this formalized C. We can do that by using the formal ISA spec to produce a formalized binary. So this is a representation of the binary in the mathematical logic. In our process, we decompile that into a more high-level graph language. We provably correct compile the formalized C down to the same abstraction level, and then we prove those two programs bit by bit equivalent using SMT solvers. We have done that before on ARM, and there's a bit of hand waving required because certainly at the time we did it, there was no formalized spec. And even now that there is a formalized spec, it's sort of retrofitted. With RISC-V, the formal ISA spec is the master, and we will hopefully eventually get hardware that is proof correct against this formalized ISA spec, and then we get a complete proof chain that goes into the hardware. And this is a real exciting prospect. Okay, so much about the proofs of seL4 and RISC-V and what they mean. How can you use it? Well, I said already, seL4 is open source. Under RISC-V, you can download it from GitHub/seL4. Everything is there. The kernel source is there, but also all the proofs. And that's, again, totally unique. However, you need to keep in mind that this is not something like Windows or so. It's an operating system microkernel, doubles as a hypervisor, not a complete operating system. So the kernel contains very little. It basically provides you strong isolation between components and controlled communication. Everything runs on top. So a nasty way of saying that, it's BYO device drivers and file systems. It's not quite as bad. There's a lot of open source components around there. On the seL4 GitHub, others provide them themselves. But also there is a growing number of complete operating systems designed for the embedded space that are based on seL4. One of them is this Trendos operating system from Hensoldt Cyber, a German company. So they have a complete OS geared towards embedded systems application based on the verified seL4 microkernel. And what the exciting thing is about their OS, they have core components of their OS verified as well. In particular, the secure boot process, and the key store. And they're working on verifying other critical components of the overall system. So this gives you a very high assurance from the microkernel into the operating system layer. The other thing that's exciting about TrendOS is it runs on Hensoldt Cyber RISC V processor, which is based on the open source Ariane, which comes with a supply chain security story using what's called logic obfuscation. So they basically encrypt the circuit in a way that's very hard to reverse engineer to protect against attacks while this chip is manufactured in a untrusted fab. Hensoldt Cyber will be happy to talk more about this. There's other people around. For example, at the microchip stand, you will find people from DonorWorks who are experts in building systems with seL4. Talk to them as well. They can help you build your system. There's other people in the seL4 Foundation, other companies that will help you build systems with seL4. So in summary, seL4, it's born 11.5 years ago, has been defining the state-of-the-art and trustworthy operating systems for now over 11 years. And now it's proof correct on the RISC V as well, bringing this high assurance story to the RISC V architecture. There's plenty more material out there about seL4. Go to the seL4.systems website, you'll find everything there. I particularly recommend the seL4 white paper, which is written to be very approachable by a general audience with a reasonable computer science background. And it tells you in more detail what seL4 does and doesn't and what its assurance story means. And there is the seL4 Open Source Foundation, which is tasked to develop and enhance the seL4 ecosystem and ease and spread its deployments. And with that, I'm happy to take any questions you might have. Thank you very much.